Wittig reaction. Wittig reaction is one of the ways that you can synthesize alkenes. An aldehyde or ketone can react with ylides. So this is an ylide to give alkenes and phosphine oxide. Now in this reaction, the doubly bonded oxygen is going to get interchanged with a group that is doubly bonded to phosphorus. So this oxygen and this group is going to get exchanged in the product, and that's how you'll get alkene. Here's the structure for phosphonium ylide. Ylide is generally a compound with opposite charges on adjacent atoms, which already have complete octet. Now, because phosphorus has the ability to have more than 8 valence electrons, we can push these electrons to form a double bond between phosphorus and carbon. So this would be the other resonance contributor of ylide. Ylides can be prepared through an SN2 reaction between triphenylphosphine and alkyl halide. You need to make sure that you have the required number of carbons in the alkyl halide. So triphenylphosphine will now act as a nucleophile, attacking this electrophilic carbon, thrusting the leaving group out, and this is going to result in an intermediate. So here is the intermediate. Okay. In this intermediate, this hydrogen right here is sufficiently acidic, so it can be pulled by a strong base such as butyllithium. Let's separate the hydrogens here. I'm going to separate these two hydrogens here. And we do have a single bond right there. So this butyllithium will go and grab this hydrogen and pushes these electrons for carbon to have it. And that's how you will form the ylide. Let's take a look into the mechanism for the Wittig reaction. The Wittig reaction is an example for 2+2 cycloaddition reaction, which means there are going to be 2 electrons involved in both of these reactants. So 2 electrons from carbonyl compound and 2 electrons from the ylide. 2 plus 2 equals 4 electrons. That's going to participate in the cyclic transition state. The mechanism is super simple. First, the nucleophilic carbon of the ylide is going to add to the electrophilic carbon of the carbonyl group. So this nucleophilic carbon of ylide is going to make a nucleophilic attack on the electrophilic carbon of the carbonyl group and thrust these electrons onto oxygen. But since this is all taking place in one step, remember this is a concerted reaction. These electrons from the pi bond will now go and attack the electropositive phosphorus. This is going to result in a cyclic intermediate called as the betaine intermediate. So let's draw the structure here. Now in the next step, triphenylphosphine oxide should be eliminated, for which the bond between carbon and phosphorus need to break, and it will move towards the carbon-carbon single bond to form a double bond. And this carbon-oxygen bond is also going to break, and it will move towards the phosphorus-oxygen single bond to form the double bond. So this is going to result in our alkene and also phosphine oxide. Let's say that you wanted to synthesize this particular terminal alkene. Okay, for which you are taking 2 different starting materials and you're reacting it with hydroxide ion. So for the first reaction, we have a tertiary alkyl halide. So this is a tertiary alkyl halide. Tertiary alkyl halides do not undergo substitution, right? It can only undergo elimination. So in which case, this hydroxide ion will go try to find the beta hydrogen. Now in this compound, we do have 2 different types of beta hydrogens. So here we have one type, and on this carbon, we have 3 hydrogens. That would be another type. But between these 2 hydrogens, obviously the hydroxide ion will go and abstract this hydrogen, pushes these electrons to form a double bond and thrust the leaving group out to form this compound. Because this compound right here is the Zaitsev product, right, which is a highly substituted alkene. And therefore this compound, which is obtained by abstracting this beta hydrogen, will be formed as a minor product. Don't forget that there are 2 hydrogens here. Let's take a look into the next reaction. For the next reaction, we are having primary alkyl halide as the starting material. Primary alkyl halide, when they react with hydroxide ion, obviously it's going to undergo substitution. It's going to give more of the substitution product and less of the elimination product. So here again, you're not able to form this terminal alkene, the desired terminal alkene. But when you employ Wittig reaction, you can easily form this alkene, for which you're going to take cyclohexanone reacted with a ylide, in which case the oxygen and the group that is attached to phosphorus in an ylide are going to get exchanged to form the only alkene, methylene cyclohexane. So Wittig reactions are useful in the synthesis of terminal alkenes, which are otherwise difficult to synthesize.